Welcome to the Deep Dive. Today we're digging into notes from Kesser and Steen's Nature and Innovation class. We're talking fungi, the good, the bad, and the very, very deadly.
That's right. We're focusing on insights from a guest lecture by someone they called Fungi Paul. He talked about lethal invasive mushrooms showing up in cities. So our plan is, first, look at the chemistry of the deadliest mushroom out there.
Okay.
Second, explore why some cultures fear fungi, this idea of mycophobia. And third, uncover this hidden danger, how fungi act like biological vacuum cleaners for environmental toxins.
And we're starting right at the top with the DeathCap, Amanita phalloides, or Grinflu's vamp. You mentioned it's the most dangerous.
By far. It causes the vast majority of fatal mushroom poisonings pretty much everywhere it grows, Europe, North America included. And to really get how sneaky it is, we need to talk about a specific, quite horrific case.
I think I know the one you mean, from Australia.
Exactly. The beef Wellington poisoning. Just awful. A woman used wild mushrooms she'd gathered, thinking they were safe, put them in this, classic fancy dish.
Right, beef Wellington, not some obscure recipe.
No. And it led to multiple family members dying agonizing deaths. She'd mistakenly picked Amanita phalloides.
It's chilling because it highlights how easy that mistake can be. Fungi Paul apparently really stressed this point in the lecture. A slight difference in appearance.
A tiny difference
It's right.
between a meal and a fatal poisoning. It kicked off this huge police investigation, became a massive news story globally, really drove home the danger for people who maybe hadn't thought much about wild mushrooms before.
So what makes this mushroom, the DeathCap, so uniquely lethal? You mentioned chemistry.
It comes down to one specific type of toxin. It's called amatoxin.
Amatoxin. Okay.
Yeah.
And what is that exactly? The notes mention it's an octopeptide.
Yeah, think of it as a small, very specialized molecule, a chain of just 8 amino acids. Small is important here. It gets absorbed really quickly into the bloodstream.
And goes where?
Straight to the vital organs. The liver is the primary target.
Why the liver?
Because the amatoxin molecule fits perfectly into a crucial enzyme in our cells, RNA polymerase II. It's like a key in a lock.
And what does that enzyme normally do?
It's essential for life. It reads your DNA to make proteins. Everything your cells do relies on this process. Amatoxin jams that enzyme, stops it cold.
So no new proteins.
Exactly. Liver cells can't repair themselves, can't function, they start to die off. That leads to liver failure, which is often what's fatal.
And Fungi Paul apparently hammered this point home.
Yeah.
You can't cook this toxin away. Boiling, drying, none of it works.
Nope. Makes absolutely no difference. The chemical structure of amatoxin is incredibly stable, and that's probably why it evolved to be tough, to survive in the soil, resist bacteria.
That stability is its weapon.
And that resilience means it survives cooking perfectly well. If you cook a DeathCap, it's still a DeathCap, still just as lethal.
Which makes identification the only line of defense. So what are the absolute must-know features to avoid it?
Okay, 3 key things Fungi Paul would have highlighted. First, look for scales on the cap, although sometimes they can wash off in the rain, so you can't rely on that alone.
Okay.
Second, a distinct ring, like a little skirt, on the stem. Many mushrooms have rings, but the DeathCap's is usually quite prominent.
Right.
But the most crucial part, and the one people often miss, is at the very base. The mushroom grows out of an egg-like sac called a vulva. It's the remnant of a veil that covered the young mushroom.
And this vulva stays at the base.
Yes, it forms a cup or sheath-like structure right where the stem comes out of the ground. Often it's partly buried, so you have to dig around the base carefully. If you just snap the mushroom off, you'll miss it.
And missing it could be fatal.
Absolutely, because if you see that cup at the base, along with the other features, greenish cap, white gills, white spores, the ring, you know you're dealing with something extremely dangerous.
And then there's the look-alike problem.
Yeah.
Fungi Paul mentioned Amanita citrina, the false DeathCap.
Right. It looks similar, especially the yellowish versions. It's not deadly, but it's not considered edible either. It adds another layer of confusion.
So the rule has to be, any doubt at all.
Any doubt, you walk away. Or better yet, you assume it is the deadly one. Mushroom ID isn't a close enough game. The stakes are just too high.
That danger really feeds into the cultural side, doesn't it? This idea of mycophobia. Fungi Paul talked about Vancouver before the 70s.
Yeah, he described a dominant attitude, largely from Anglo-American settlers, of just general fear and suspicion of wild fungi. Anything growing wild was basically a toadstool, something potentially poisonous, best left alone.
So mycophobia, a cultural fear.
Pretty much. Unless it was bought in a store, prepackaged, it was suspect.
But here's the weird part from the notes.
Yeah.
At the same time, Vancouver apparently had the highest per capita consumption of cultivated mushrooms in the world, those white button ones.
It's a fascinating paradox, isn't it? Total rejection of the wild, unfamiliar fungus, but a huge appetite for the known, safe, cultivated agaricus. It shows the fear was specific to the unknown wild element.
Not fungi themselves, just the ones they didn't control.
Exactly. Compare that to places like Italy, which Paul also mentioned. There, foraging isn't some niche hobby, it's deeply embedded in the culture. Generations of knowledge passed down.
So in Italy, it's less fear, more respect, based on knowledge.
Precisely. They know the woods, they know the seasons, they know the lookalikes, they know how to prepare them safely, which brings us to another key point from Fungi Paul for the class, this safety paradox.
Okay, what's that?
As foraging became more popular, especially in places without that deep cultural knowledge, reports of mushroom poisoning actually went up. But, and this is important, most weren't the deadly Amanita poisonings.
So people were getting sick, but not usually dying.
Right. It was what's called abnormal poisoning, often caused by eating common, known edible species that were maybe old or contaminated with bacteria, or critically eaten raw.
Raw? I thought some mushrooms were eaten raw, like in salads.
Some cultivated ones, maybe.
Yeah.
But Fungi Paul stressed, and it's a golden rule for foragers, wild mushrooms should always be cooked. Always.
Why is that so absolute?
Think about kidney beans. We know you can't eat raw kidney beans, right?
Yeah.
They contain lectins, which are toxic unless destroyed by heat.
Okay. Yeah.
Well, many edible wild mushrooms contain compounds that are mildly toxic or just really hard to digest when raw. They might cause gastric upset, cramps, things like that. Cooking breaks those compounds down.
So heat isn't just for flavor, it's a safety measure. It's neutralizing the mushroom's own defenses.
Exactly. Frying, boiling, sautéing it denatures those potentially problematic compounds. So the clear message has to be, if you forage, you cook. No exceptions for wild mushrooms.
That idea of chemical defenses is interesting. Paul used this analogy, fungi coating themselves in chemicals like rust-proofing.
It's a good way to think about it. They live in damp places, constantly under attack from bacteria, other fungi, insects, slugs. They need protection. Those chemicals are their armor.
And amatoxin is just one very potent example of that armor.
A very extreme example, yes. It likely evolved as a broad defense, stopping protein synthesis in whatever tries to consume or compete with the mushroom. It wasn't specifically targeted at humans, we just happened to be susceptible.
But not all fungi use defense, right? The notes mention stinkhorns and truffles doing the opposite.
Right, a totally different strategy. They want to be found. Stinkhorns produce these, well, stinky smells, often like rotting meat, to attract flies.
Ooh, why flies?
The flies land, pick up the sticky spore mass, and fly off, spreading the spores elsewhere. Truffles use appealing scents to attract animals like pigs or dogs to dig them up and eat them.
And spread the spores through digestion.
Exactly. Through their droppings, it's all about getting the next generation dispersed. So some repel, some attract, using chemistry either way.
Okay, that's the visible chemistry. But Fungi Paul also talked about an invisible chemical danger, especially relevant for us today, heavy metals.
Yes. This is crucial, especially if you're thinking about foraging anywhere near urban areas, roads, old industrial sites, even some agricultural land. Fungi are incredibly efficient at absorbing things from their environment.
They have a huge underground network, the mycelium.
Exactly. Massive surface area designed to suck up water and nutrients, but it also sucks up heavy metals present in the soil, things like lead, mercury, cadmium. They're like biological vacuum cleaners.
And unlike amatoxin, where you get sick fast, heavy metals build up slowly.
That's the insidious part. No immediate symptoms. You could eat mushrooms harvested from a contaminated spot for years, accumulating these metals in your body without realizing it.
Which makes foraging near potentially polluted areas really risky.
Extremely risky. And this links back to something we touched on earlier, how the body deals with toxins over time. Remember the cell turnover idea?
Right, that the body replaces cells at different rates, some fast, some slow.
Exactly. If you ingest, say, too much manganese or cadmium, your body tries to get rid of it. Cells in your gut lining turn over quickly, maybe in days, so some might get flushed out that way.
But if it gets stored elsewhere?
If it gets incorporated into bone cells or nerve cells, those cells stick around for years, even decades. The metal just sits there. Elimination becomes a very, very slow process. It forces us to think about exposure on a timescale of years, not just days or weeks.
That's a sobering thought. And this accumulation happens partly because of chemical confusion. Paul talked about fungi mistaking one element for another.
Yes, it's like chemical mimicry or identity theft at the molecular level.
Yeah.
Fungi need certain elements to live. Potassium, for instance, symbol Ca, is absolutely vital for cell function.
Okay.
Well, cesium, including radioactive cesium isotopes that can be environmental contaminants, behaves chemically almost identically to potassium.
So the cell's machinery, the little protein channels designed to grab potassium.
They can't easily tell the difference. They grab the cesium too, pulling it into the fungal cells, where it can accumulate to dangerous levels, especially if it's radioactive.
Wow. And a similar thing happens with sulfur and selenium.
Exactly the same principle. Sulfur is essential, used in amino acids like cysteine and methionine, which are building blocks for proteins. Selenium sits right below sulfur on the periodic table, so it has very similar chemical properties.
So the fungus accidentally uses selenium instead of sulfur when building proteins.
It can, yes. It forms what are called selenoamino acids. The protein still gets built, but the selenium atom behaves slightly differently than a sulfur atom would. It might change the protein's shape, its stability, its electrical properties.
Paul apparently used an analogy, like the protein is speaking with an accent.
That's a great way to put it. The protein still functions, mostly, but it's subtly altered. This chemical confusion allows fungi to gather what they need, but it's also how they end up concentrating heavy metals and other elements from the soil, making them potentially hazardous for us.
Let's shift back to that urban environment Paul was discussing with Kesser and Steen. Cities are trying to bring nature back parks, greenways. But this can unintentionally open the door for invasive species.
It's a major consequence. When you move large amounts of soil, trees with their root balls, mulch, you're potentially moving fungal spores, insects, seeds from somewhere else.
And these newcomers can take over.
They often do. They might form new symbiotic relationships or change the soil chemistry in ways that favor them over the native species. It disrupts the existing ecosystem.
The notes mention a really stark example: Chinese truffles turning up in Italy.
A huge problem there, economically and culturally devastating. These invasive Chinese truffles look a bit like the highly prized native Italian white and black truffles.
Which are worth a fortune.
Exactly. But the invasive truffle's mycelium spreads underground, changes the soil conditions, the relationships with the tree roots, and makes it difficult or impossible for the native truffles to grow there anymore.
And you can't just weed them out.
Not easily. Fungal spores are microscopic and incredibly persistent. They can survive in the soil for decades. Once an invasive fungus like that gets established, it's almost impossible to eradicate. It's like invisible long-term pollution for that specific ecosystem and the truffle economy.
It sounds like this underground world is a constant competition. Paula said it all comes down to the quest for carbon, sugar.
That's the fundamental currency. Energy. Fungi need carbon to grow and reproduce, just like us. They get it in two main ways.
Strategy one?
The peaceful route. Mycorrhizal fungi. They form partnerships with plants. The fungus gives the plant water and minerals it gathers with its extensive network.
And in return?
The plant gives the fungus sugars, carbon compounds it made through photosynthesis. It's a trade, a symbiosis. Both benefit.
Okay, that's the cooperative way. Strategy two.
More aggressive. Saprophytic fungi. They are the decomposers. They break down dead organic matter, fallen trees, dead leaves, animal remains. They use powerful enzymes to chemically unlock the carbon stored in that material.
So the traders and the decomposers. What happens when their networks meet underground?
It's not friendly. They chemically sense each other's presence. They often release toxins or enzymes to attack or inhibit their competitors. It's a constant, unseen battle zone under our feet.
A war for resources.
A war for that stream of carbon and energy. And this intense competition is likely one of the driving forces behind the evolution of potent toxins like amatoxin weapons in that underground chemical warfare.
It really paints a different picture of the forest floor. So, wrapping up this deep dive, which started with Kesser and Steen's class notes, we've gone from a deadly beef Wellington to chemical warfare underground. Fungi are clearly vital, complex, but demand respect.
Absolutely. They are master chemists, essential recyclers, but their survival strategies involve potent defenses and this incredible ability to absorb almost everything around them, nutrients and toxins.
And that links back to the final thought you wanted to leave us with, connecting that slow accumulation of metals to how our own bodies handle things.
Yeah, just reflecting again on that timescale. When we encounter persistent contaminants, whether it's heavy metals from fungi or other environmental pollutants, Our bodies do have amazing repair and purging systems, but they often work on the rhythm of cell turnover.
Days for some cells, years for others.
Exactly. So elimination isn't always fast. Thinking about health risks, especially from environmental exposure, really requires considering that long-term perspective, that rhythm of years.
Oh,
It puts our connection to the environment right down to the soil chemistry into a different
a
light.
powerful reminder. Okay, one last very important point from the source material, a necessary disclaimer.
Crucial, yes. This discussion, this deep dive, it's based on lecture notes and research. It is not expert advice for identifying mushrooms or treating poisoning. We are not mycologists or doctors.
Absolutely. If you choose to forage, and you or anyone you're with feels even slightly unwell after eating wild mushrooms,
Don't wait, don't guess. Contact a doctor or your local poison control center immediately. Time is absolutely critical in potential mushroom poisoning cases.